In this video, we're going to look at the forces on 2 kilograms of water while the water is swung in a vertical circle at a distance of 88 centimeters from my shoulder at a speed of 1 cycle per second. And there was 2 kilograms of water in there, and we're going to analyze why that was possible and how much force had to have been on the water at each point in the circle. As you saw in the video demonstration, we have a man swinging a bucket in a vertical circle. That bucket of water has a mass of 2 kilograms. It's moving at a constant speed and it's 88 centimeters from the shoulder. It's going at a frequency of 1 cycle per second. So I'm going to answer these questions. What's the speed of the bucket? What is the acceleration? What's the tension in his arm? That is when it's at the top. So let me just quickly correct that there. What is the tension in his arm at the top? What is the tension in his arm at the bottom? So that's when the bucket's all the way at the bottom. And then what's the tension in his arm when the bucket is 40 degrees from the bottom? So first off, let's find the speed of this bucket. So what we do know is that the circumference is 2 times pi times the radius, and our radius is 88 centimeters, which is 0.88 meters. So we have a circumference of 5.529 meters. And if it's going at 1 cycle per second, that means that the time it takes to go all the way around is 1 second. So that's going to make our speed equal to 5.529 divided by 1, which of course is simply 5.529 meters per second. Now, what is the acceleration? The acceleration is towards the center. This is moving in circular motion. So we have centripetal acceleration. And our centripetal acceleration is going to be v squared divided by r. The square speed divided by the radius. So it is 5.529 squared divided by 0.88, which is 34.7. So that's 34.7 meters per second squared. So if you're wondering what I did, I took this value and put it here, and I took the given radius and put it there at the bottom. That's where that number came from. So that's the centripetal acceleration of the bucket. And we're now in a position to answer a couple other questions, such as what is the tension in his arm at the top, and what's the tension in his arm at the bottom? Now, the dynamics of a body that's moving in a circle is it's going to have a force. We call that the centripetal force. That'll be the net force on the object. It's always towards the center of the circle around which it rotates. And as always, F equals ma, so centripetal force is the mass times the centripetal acceleration. Now the mass is 2 kilograms, and the centripetal acceleration is 34.7 meters per second squared. So that's going to give us a net force, a centripetal force of 2 times 34.7, which is 69.4. So we have 69.4 newtons of force always going towards the center as the bucket makes its way around. So how much force is the arm exerting when it's at the top? Well, let's consider when the bucket's at the top. So when the bucket's at the very top, it has gravity pulling it down, and gravity is 2 times 9.8. We're assuming we're on the Earth. So that's going to be 19.6. And it also has the tension in the arm pulling it down. So this picture here, this circle up here is the bucket. This is my shoulder. And you're looking at the bucket swinging around my shoulder, and it's at the top at this moment in time. And let me just label that, so we're at the top. So when it's at the top, you know that the net force is the centripetal force, and that's going to be equal to the force of gravity plus tension. That means that the tension when it's at the top is the centripetal force minus the force of gravity. Because gravity is pulling the bucket down, plus tension in the arms pulling the bucket down. So the centripetal force is still 69.4. For this to move in uniform circular motion, it'll always be 69.4. And we're going to take away from that the 19.6 newtons that gravity is helping us with, leaving us with 49.8. So we have 49.8 newtons of tension when it's at the top. Now let's consider when that bucket's at the bottom. So we've gone all the way around and our bucket is now at the bottom. There's your bucket, there's your arm, there's the shoulder. So we have tension in the arm, that's going up. The force of gravity is going down, and the net force is the centripetal force, and it's towards the center, so right now it's going up. So that's, sorry, I'm missing the F there. The centripetal force is going upward, and that is the net force. So what does that mean? That means that tension minus the force of gravity is equal to the centripetal force, because they're in opposite directions now. So now tension is going to be the centripetal force plus the force of gravity. See what's happening here? When the bucket's at the top, tension and gravity are going the same way, so the tension you feel in your arm is less. When the bucket's at the bottom, tension's pulling up, but gravity's pulling down, and because they're opposing each other, and yet you still need to end up with the same centripetal force as your net force, they're going against each other, the tension becomes much greater. So that bucket is going to feel like it's heavier when it's at the bottom. It's going to be pulling more on your arm at the bottom than it is at the top. And our centripetal force is, where is it now? It's 69.4, and gravity's 19.6. So this is 69.4 plus 19.6. I apologize for the wait. It's getting dark here now, and my solar-powered calculator's taking time to warm up. Here we go. It's 69.4 plus 19.6. It is 89 newtons. So as we take that 2 kilogram bucket and we swing it in a vertical circle at a constant speed at a rate of 1 hertz, when it's at the top, we feel 49 newtons of tension, essentially 50 newtons of tension. But when it's at the bottom, we feel almost 90 newtons of tension. Because when it's at the bottom, we've got to go against gravity to accelerate it towards the center, which is required to move it in a circle. And when we're at the top, gravity's helping. You see, when it's at the top, gravity is helping move it in a circle, because accelerating towards a central point causes circular motion. That's what gravity is doing. That's why the water is not falling out of the bucket. It's still falling down, but the bucket's falling down with it. The arm and everything else is falling down with it. That's why I was able to stay dry while swinging that in a vertical circle. Okay, so I've shown you how to find the speed of the bucket, and we found the speed by taking the circumference, the total distance that that bucket traveled, divided by the amount of time it took for a full circle. We then found the acceleration using the formula. Centripetal acceleration is v squared over r. It's the square of the speed divided by the radius. We then found tension in the arm when the bucket was at the top, where gravity's pulling down and tension's pulling down, and together they have to give you the centripetal force required for the given centripetal acceleration, or the calculated centripetal acceleration. And we found the tension when the arm was at the bottom. Now, when the arm's at the bottom, gravity's pulling down, tension's got to pull up so great that it not only overcomes gravity, but also accelerates it towards the center for the uniform circular motion. Now we're going to consider tension when the arm is 40 degrees from the bottom. When the bucket's at 40 degrees, we run into a problem. The problem is this: can the bucket move in uniform circular motion as the person is swinging it? The answer is yes, it can. That bucket can move at a constant speed. However, in order for that to happen, tension cannot be the only force that the person is exerting on the bucket. You see, it was a mistake of mine to pose the question the way that I did. Let me explain the problem with it, because there's something to learn from here. So I'd asked a question where we have a guy swinging a bucket of water around. So there's the bucket of water, there's the man's shoulder, and the bucket is traveling in a circle. And I said, to simplify things, let's assume it's moving at a constant speed. So we have uniform circular motion. I gave the frequency. And I've asked you to find the tension at the bottom, to find the tension at the top. And both of those are quite all right, because the only force exerted by the person's arm and shoulder on the bucket when it's at the bottom and when it's at the top would be tension. However, I asked you to find the tension when the bucket was part of the way up or part of the way down, when it was at 40 degrees from the bottom. And then I tried to solve the problem. A student of mine also tried to solve the problem and found an error in my solution and couldn't quite solve his. And here's why. When we're at an angle, if the only force is tension, which is going this way, then through conservation of energy, while that bucket's on the way up, it's going to slow down. While that bucket's on its way down, it's going to speed up. The only way that we can get that bucket to move at a constant speed is if, when it's on the way up, not only do we exert tension on it, but we also have a force rotating the arm that way. And if you just swing a bucket around like I did in the demo video, you'll feel that. You'd have to have a force rotating the arm in addition to pulling. And without accounting for that force, we can't just solve the question as simply as it was with tension. So I'm going to remove that question from you guys for now. When I have a bit more time, I'll go through a full solution that'll involve not only the force of tension, but also the rotating force. So that would actually be the torque. You would have to, at the shoulder, apply torque to your arm to get it to rotate upwards, in addition to pulling it towards the center to get the bucket to swing around at a constant speed, as you saw in the video. So when we get to a unit on torque, we'll come back to this very same question, but you can just leave it for now. Scratch it off the question list, and my humble apologies.